Welcome to this video on universal gravitation. We will explore how Kepler's observations and Newton's synthesis shaped our understanding of the mechanics of the cosmos, connecting the motion of planets to the falling of an apple. The quest to understand the heavens evolved over centuries. From Ptolemy's geocentric model to the heliocentric paradigm of Copernicus and Aryabhata, the field advanced through Brahe's precise data, Kepler's laws, and Galileo's experiments on falling bodies. Kepler defined planetary motion through three laws. Planets move in elliptical orbits with the sun at one focus, they sweep out equal areas in equal times, and the square of the orbital period is proportional to the cube of the semi-major axis. The law of areas is tied to the conservation of angular momentum. Because gravitation acts as a central force, a planet must travel faster when it is closer to the sun at perihelion, and slower when further away at aphelion. Newton's law of universal gravitation unified terrestrial and celestial mechanics. He proposed that every body in the universe attracts every other body, a force proportional to their masses and inversely proportional to the square of the distance between them. In 1798, Henry Cavendish conducted a famous experiment to quote, weigh the Earth. By measuring the tiny gravitational force between lead spheres, he determined the value of the universal gravitational constant, g. We can derive local acceleration due to gravity, or g, by combining Newton's laws. This math confirms Galileo's observation. The acceleration of a falling object is independent of its own mass and depends only on the Earth's mass and radius. It is important to distinguish between big G and little g. Big G is the universal constant representing the fundamental strength of gravity, while little g is the local acceleration we experience, which varies based on location. Gravity also varies with altitude and depth. As you move further from the Earth, gravity follows an inverse square law and decreases. Moving toward the Earth's core, the acceleration due to gravity decreases linearly until reaching zero at the center. Gravitational potential energy is the work required to bring a mass from infinity to a point in a gravitational field. Because gravity is an attractive force, this potential energy is expressed as a negative value within the gravity well. To break free from Earth's gravity, an object needs a specific escape speed. By ensuring its total energy, the sum of kinetic and potential energy, equals zero, we find that for Earth, this speed is 11.2 kilometers per second. For satellites in orbit, the centripetal force is perfectly balanced by the gravitational pull. This relationship allows us to calculate the orbital speed and the time period required for a satellite to complete a single revolution. An orbiting satellite possesses both kinetic and potential energy. Because its total energy remains negative, the satellite stays bound to the Earth. If that total energy were to reach zero or higher, the orbit would break. In summary, the laws of gravitation provide a blueprint for understanding the universe. From the fall of an apple to the motion of satellites, one singular framework governs the architecture of the cosmos.